Good evening or good morning, everyone. I'm Roberto Miele, and I'm a PhD student in University of Lisbon in Technical, and I will be your co-host together with Turan Guglielmo. And I will now pass the word to Turan. We will have 3 sections, and well, as you know, the presentation will be there will be 10 minutes for the presentation plus 5 minutes for any question. Now, Turan, I will pass the word to you.
Hi, everyone. Good morning or good evening. My name is Turan and I'm from Azerbaijan. And so thanks to Roberto for talking about agenda and what we will go through. And from my side, I'm wishing you good luck. Yeah.
All right. So for the first session, we have seismic application. I will be the session chair together with Caterina Lacatuso. And as a first presentation, unfortunately, Mohammad Al-Mubarak won't be able to present. So Jonovan Iseltik will be the presenter for his job as his colleague, as his university colleague. So I think you can already start with the presentation. You're muted.
All right, thank you, Roberto. Can everyone see my presentation?
Yes, we can.
Okay, perfect. So unfortunately, indeed, Mohammed couldn't make it today. So instead, you'll be stuck with me today. So Mohammed is a master's student at Delft University, and I'm a PhD student there. And basically everything, so this is my first disclaimer, everything I'm going to show today is Mohammed's work, and I'm just here to take the credit for it. So the title of this presentation is Plane Wave Machenko Imaging, a Field Data Application. And some of these words might look like gibberish to you. Other words, I guess you will be quite familiar with. And what I'm going to do in this presentation, I'm first going to unravel the mystery behind this first block, the plane wave Machenko imaging. Again, I guess everyone has some ideas of plane waves, some ideas of imaging, but this Machenko might be really unfamiliar to you. And then for the second part of my presentation, I will show you what Mohammed actually did with this method and how he applied this to a field data set. So first, why do we have Machenko? What even is Machenko? And why do we care? So this is the ideal seismic data set. You see you have a source at your surface, and then you send in your wave field. Your wave field bounces back nicely on all these reflectors in the subsurface. And once it comes back to the surface, you receive your wave field, and beautiful, you have seismics, problem solved, let's go, or go home. Unfortunately, in reality, this is not always this easy, because what you will see is that you have internal multiples that also are generated in the subsurface. And what these internal multiples do is they can obscure the view of subsurface targets for you. So you want to really see the primary response from your reflectors, but because of these multiples, you might not be able to accurately see all the reflectors accurately. You might actually think there is an additional one because of these multiples and so on. And this is actually where the Machenko method comes in. So for the Machenko method, we will now define a focal depth. Basically, in the example I'm showing you today, this focal depth will be at around 900 meters. And we are going to insert some kind of wave field that focuses our wave field at this focal depth. So this is called a focusing function. And this focusing function is defined in a truncated medium. So everything below the focal level, we basically ignore, or we assume it's to be homogeneous. And that all sounds very complicated when I'm saying it out loud, but systematically, this is basically how that looks like. So So basically what you see is we have the same medium, except below this 900 meters of depth, we no longer have any other structures or reflectors anymore. So it's homogeneous here, as you can see. And another thing you see is that the wave field that we inject, so that's the wave field in red, is actually generated in such a way that it focuses at this focal point here at the depth, and it doesn't have any other effects from the overburden. So usually you would have reflectors here that would go down again and go up again. But because the way that this focusing function is constructed, we actually eliminate all these reflections by adding additional terms in our focusing function. So that's basically what you see here. So this is the normal function, but here we add additional events to cancel out all these internal multiples and get a nice impulse response at this depth. And so this is basically the idea behind the Machenko method. And this is it in equations, which looks a lot worse, but will carefully and slowly take you through these equations. And hopefully at the end of it, you will have some understanding of it. But basically what you can see, these are two coupled equations. So you have a first equation up here, a second equation up here, and basically the output of the first equation, so on the left-hand side, will be used as input in the second equation. And vice versa, the output of the second equation will be used as input in the first equation. So that looks all like mathematical magic. How is it actually working in practice? So now what we are going to do is the focusing functions that we defined before, you can see it here again, we actually insert it into our physical medium. So basically, we don't have this truncated medium anymore, we have our physical medium. And now we can see a number of things. So basically this focusing function that we insert, which is colored red, and also in this equation it's red. So what we do is this focusing function is defined as focusing at point A, and it originates from points XS. So these are basically coordinates, focusing coordinate, and the origin coordinate. And what you can see is this is a convolution in this case, and a convolution with the reflection response of the medium. So the reflection response is measured at the source coordinates XS and received at the receiver's coordinates XR. And effectively what we do is this means that we insert this function into our medium, as you can see in the systematic drawing over here. And now what we receive, what we get back, is an upgoing focusing function. So that's the focusing function in blue, and a Green's function, which is defined as it excites at the focal depth and it's received at the surface. So excited at XA and received at the receivers at the surface. Sorry. This is basically the first equation for the Machenko method. And the nice thing about this is that these two equations are perfectly separated in time. So you'll have a causal requirement that basically separates the Green's function from the focusing function by a certain time. And in this systematic drawing, you can kind of see this as well, that these are clearly separated and they don't crisscross through each other. And then we also have this second equation. And basically what we do now is we inject the received focusing function that we got from the first equation. We insert it, backpropagate it, so reverse it in time, and then we inject it in the same medium. And then again, we see that we retrieve a focusing function and a Green's function. And again, these are more or less only the first event, as you can see here, is shared, but all the other events will be perfectly separable in time. And basically what you see now is that you have two Green's functions that are excited from your focal depth. And this allows to redatum your source. So previously we had a source at the surface right here. And now after this process, we actually see that the source has been redatamed to this focal depth, but the receivers are still at the surface. Now we can apply a second step, and obviously the second step is actually going to redatum the whole wave field. So you see now in the second step, we no longer measure the wave field at the surface, we measure the wave field at the focal depth. And what this effectively has done is you have removed the whole overburden effect from this reflection. And so you no longer have to deal with this annoying internal multiples that I showed you at the start of this presentation. And now where do these plane waves come in? Well, one drawback of this is that for every focusing point, you would have to individually calculate your response, apply the Machenko method, and it's actually quite computational expensive. So it would be better if we could do for one focal level, we could do this whole process at once. And that's what we achieve by using these plane waves. So these plane waves are basically a superposition of all these focusing functions, and there are this is a little bit two different ways of how to generate them. You can put your sources at a tilted angle, or you can delay the time at which the sources excite their wave field. And so that's basically what you can see in this figure. But the idea is just that you can combine all these point sources into a single plane wave. And that's what we show here. So we have multiple focusing functions, and effectively we create now a focusing function that focuses a plane wave at the focal depth. And these are the functions. They are basically exactly the same, only now they have these tildes on top of all the responses, and these tildes indicate now we're dealing with plane waves. And again, we can see we focus this wave field, we get the Green's function and a focus function. So here you can see the Green's function that we get. It's exactly the same principle as we saw before. And similarly, we can also get the second Green's function using exactly the same principle. And of course, we can also redatum our receivers again to this focal depth. And now we effectively did exactly the same procedure, but because we used plane waves, we actually have this whole focal level at once, and we only need to do this for one. Well, we only need to apply the Machenko method once for this whole focal level instead of doing it for each point at the focal level. So that's where the computational benefit comes in for the plane wave method. And basically, this is the method that we use, and then we can now extract the responses from focal levels. We do this for each level in your medium. So you start at the top at depth 0, and then for each depth, I think we use an increment of 10 meters. So for each 10 meters, we apply this Machenko method, a plane wave Machenko method, and we generate results, and we generate a multiple free image. So we tried this on a data set. This is a data set above the Voring Basin, shot by Statoil, and it's currently, formerly it was Statoil, currently it's Equinor. And what you can see, this is the conventional image. So this is conventional RTM. And we highlighted some effects with the red arrows. And now what you can see, this is the plane wave image. So one thing I think is quite nice is if you look at this reflector, you see by eliminating the multiples, we can clearly see that this reflector is now way more well-defined. And you can also see that at other points. One point that I'm personally quite impressed with is if you look at this reflector here, you can clearly see that the Machenko method is weakening this. So that's the suppression of a multiple. And this is something that was also found by Zhang et al., who studied the same data set. And basically that shows us that we are indeed suppressing multiples and not doing some random gibberish with the data. So I'll show you, this is the plane wave Machenko results, and this is conventional image, Machenko, conventional, Machenko, conventional. So you can clearly see some improvements in this final image due to the multiple suppression. So this is the difference between the two. It's not that interesting for now, I don't think. So what I hopefully have taught you today is that we can remove internal multiples by applying this Machenko method, by redataming our sources and receivers to a new level in the subsurface, and that we can use this to get images that are multiple free. And the nice thing about the plane wave method is that it's less expensive, but still can be successfully applied to field data. If there are any questions, I'm ready to answer them for you. And thank you for your attention.
Thank you very much, Jono. So if there are any questions from the audience.
I have a question for you, Jono.
Yes.
If the macro velocity model is incorrect or poorly done, how will it influence the accuracy of the method?
Yeah, so that's the macro velocity model for the Machenko method is not that that important. You need for this particular method, you need a smooth velocity model, and as long as it's more or less correct, a smooth velocity model will be all right. The only thing that happens if you have the wrong velocities is that your results will be shifted up or down, but it will still be successfully eliminating multiples.
All right. I think we have a question from Monet. Yeah.
Yeah. Hello. Good morning. So please, if you can, please get back a little bit to the image. Yeah, here exactly. So in terms of interpretation, such kind of image. So can you please give up, because you have gone through it and you have give some information, but I didn't catch that. Can you please repeat that again in terms of interpretation? Thank you very much.
Okay. Yeah. So well, there is not too I personally don't know too much about the exact details of the Foreign Basin. I just know that you have, so this will be the sea bottom, so that's at 1,000 meters. And then you have some seismic events from reflectors below this basin. I personally am not a geologist, so I can't really tell you what all these different reflectors where would be the oil, where would be the gas, where would be this or that, I don't know. But what I can tell is that, for example, if you look at especially this, you see in the conventional image, you don't really have a clear structure here, while after applying the Machenko method, you can clearly see that there is now a reflector here, which would indicate that here would be a boundary between two layers in the subsurface. I hope that somehow answers your question. Might not be extremely satisfying, but.
All right. Okay. I guess we can move on.
Right. Thank you.
Thank you very much, Jono. It was very clear and very nice presentation.
For the next paper, Mehmet Ali Uci will present from Istanbul University.
You're muted.
Mehmet, you're muted.
Sorry, I forget to open the microphone. So can you see my screen?
Yes.
Yes.
Yeah, okay, thank you. Thank you so much. I would like to say hello to everyone. I'm Mehmet Ali Uci from Istanbul University, Cerrahpaşa. I'm a PhD student, and I would like to present my study about the comparison of multiple suppression by predictive deconvolution 2D dataset in the Sea of Marmara. First, I would like to give a brief information about my outline. First, I will start with my introduction and tell about why do we use deconvolution, and I will show my study area to you and the application of the method, and give my results in conclusion. and finish my presentation. To begin with my introduction, the problem is to define which domain, pre or post-stack, is better for the application of predictive deconvolution to get an accurate result, to get a better result. To solve this problem, we have to define correct parameters for predictive deconvolution, and we have to apply predictive deconvolution on both pre and post-stack domains with the corrected parameters that we have defined before. So at the end, we have to compare the results on both domains and decide the best result for it. If we go through the why do we use deconvolution, let me open my pointer as well. So deconvolution is a filtering process which removes a wavelet from the recorded seismic trace by reversing the process of convolution. The usual way to perform deconvolution is to design a basically Wiener filter to transform one wavelet into another wavelet in a least square sense. So why do we use deconvolution? Especially to suppress the surface lattice multiples, to increase the temporal resolution, and even though they're removing the considerable amount of fringiness. As you can see here in the equation, that we can easily define the multiple reflections on the seismic data while using this equation. And this equation is equals to M for multiples, S for impulse signal, R for reflection, and T for the delay time. As you can see here in the figure, that in the left side of the slide, our primary reflections came through on 100 milliseconds on the data, and our reflections, first, second, third, and even though fourth order multiple reflections came through 2, 3, 4, and 500 milliseconds on the seismic data. And if we apply a great predictive deconvolution with a successful parameters, we suppress all the multiple reflections, and we will have our desired output with only primary reflections on the data. So why do we use the predictive deconvolution? Predictive deconvolution can be used to remove the multiple energy, as I said, from the seismic data by predicting and suppressing the multiple reflections on it. And it also alters the spectrum of the input data to increase the resolution. And also, it is almost always applied to at least one to marine seismic data, even though you can use the predictive deconvolution on the land seismic data too. For my study area, the 2D multi-channel marine seismic reflection data, which is used in this presentation, is located on the eastern side of the Marmara Sea. And it is collected by General Directorate of Mineral Research and Exploration, a company from a government, and with using the research vessel of MTA Seismic 1 in 1997. As you can see, my reflection data located over here. If we can go with the acquisition parameters of the data, you can find the exact parameters for the data in this table, and you can see the raw data from shot number 349 from the section. And we can easily see that our primary reflections over here and first order and the second order multiple reflections are located over here. To go further with the flow chart of the processing, first, as you know, we will input our data to the system and we edit the data. What I mean by saying editing, that we delete the undesired traces from the data. And after that, filter and gain analyze have been applied to the data, and we define the geometry. After we defining the geometry, we have two paths to go on. The first path will be applying predictive deconvolution to the shot gathers, and we will have the results for the predictive deconvolution, and we will apply velocity analyze and dynamo correction, and we will acquire our stack section for the pre-stack gathers. But if we go the different path, like if we apply the velocity analyze and dynamo correction after we define the geometry, we will acquire our stack section, and after that we will pick the water bottom and we will define these picks to the system, and then we will apply the predictive deconvolution to stack section, and we will acquire our result section. So this will equals to the post-stack section. So to start with the applying predictive deconvolution to the pre-stack, as you know, the pre-stack deconvolution is controlled by two important main parameters, which are operator length and the prediction length. So determination of these parameters affects the predictive deconvolution results directly. So if you can see here on the raw data figure, we are going to select one trace and get its autocorrelation. And in the autocorrelation result, we will define the predictive deconvolution parameters, as I said before, the prediction lag and the operator length. So this alpha equals to prediction lag, and the M equals to operator length for this picture. So prediction lag value must be chosen equal to first period of the multiple reflection, and the operator length value must be chosen as including the multiple reflections like this time series. So you can easily see that our primary reflections and first and second order multiple reflections too on both figures as well. In press-tech shot gathers, one important point that the prediction lag parameters change with the offset, so that we have to define the parameters for the predictive deconvolution parameters for each shot gathers in all press-tech section, because to acquire a great result for it. After we define our parameters from the autocorrelation section and apply through the shot gather, we see that the surface-rated multiples are suppressed very well without affecting the primary amplitudes. As you can see, we are not seeing the first order and the second order multiples anymore. We are only seeing that the primary reflections only on our data set. So if we apply and go through with the second path, if we apply the predictive deconvolution to the post-tech section, we have to first define the water bottoms. So we have to pick the water bottom first and define these peaks to the system. And then again, we will select the trace and get this autocorrelation. And we will select the parameters as same as we did in the predictive deconvolution to press-tech section. We again select the prediction lag and the operator length, and we will apply the predictive deconvolution. There is one difference that in the post-tech sections, in the previous slides, I said that in press-tech shot gathers, the prediction lag parameters change with the offset, so that we have to define parameters for each shot. But in the stack section, since all the reflections are anemocorrected, so we have to define these parameters for each water bottom picking points, which I mean by the CDP numbers. As we picked over here, in each picks, we have to define a prediction lag and operator length parameter to get a successful result. At the end, when we apply the predictive deconvolution to the post-tech section, the surface-rated multiples are suppressed, as you can see here, but while suppressing the multiples, the primary reflections are also attenuated. So it's hard to select some primary reflections over here in this figure. So if we compare the results on both press-tech domain and the post-tech domain, we see, when we apply the predictive deconvolution on shot gathers and acquire the stack section, as you can see here in the left side of the slide, we definitely see that the multiple reflections are suppressed very well and the primary reflections are much more selectable. However, when we apply the predictive deconvolution to the post-tech domain, we see that the multiples are also suppressed, but the primary reflections are also attenuated. So it's really hard to select some of the primary reflections on the data. So to collect the results and give a conclusion about it, predictive deconvolution, as you know, is observed to be suppressing the surface-rated multiples in both pre and post-tech domains. However, the obtained result, as you saw before, are significantly different. So if we apply the predictive deconvolution on the press-tech shot gathers, the surface-rated multiples are removed without attenuating the primary reflection amplitudes, and our signal-to-noise ratio has been increased. Our resolution has been increased, and we will have more accurate result and more interpretable seismic section. But if we apply the predictive deconvolution in the post-tech section, but don't forget, which has no predictive deconvolution in application in press-tech section, the surface-rated multiples are removed with attenuating the primary reflections, and the signal-to-noise ratio has been decreased. Seismic resolution has also been decreased, and we will acquire an uninterpretable seismic section. So I would like to finish my presentation, and I would like to thank General Directorate of Mineral Research and Exploration for providing us this multi-channel seismic reflection data with the permission. And we thank to all MTA Research Vessel Seismic 1 personnel for collecting this data set. And even though the seismic data set processing steps in this study were carried out by using Paradigm Echo seismic data processing and Geodet software, we thank to also Emerson EP company for granting us to use this software with an educational license. Also, this study was funded by Istanbul University Cerrahpaşa Scientific Research Project Coordination Unit. And I would like to thank for your attention for all.
Thank you. Now, if somebody has any questions.
Well, I have a question regarding the predictive deconvolution applied to the post-tech seismic. Do you think it would be able to predict the degree of attenuation of the amplitudes of the seismic in order to attempt a sort of recovery of these amplitudes?
So it's really hard to define that one, because when we are getting the stack section from the data, as you know, we all getting all the reflections in the same point from the CDP gathers to the stack section in a one whole section. And since all reflections are anemocorrected, so it's really hard to define the primary reflections over there, even though the multiple reflections are collected together by the primary reflections. So if we apply on the deconvolution on the post-text section, it's really hard to eliminate the multiple reflections on the data. Yes, we are eliminating the multiple reflections, but we are also losing primary reflections too. And in that point, the best results is acquired if we apply for the shot gathers or CDP gathers without getting the stack section. If we apply the predictive deconvolution to the press stack and shot gathers, or in the CDP gathers from the press stack section, you know, we can eliminate the primary reflections at multiple reflections angles. So we can directly eliminate the multiples from there. So it's really easy to eliminate in the press text section too, rather than using in the post text section.
Thank you. All right.
Okay, thank you so much.
Thank you so much for the presentation. It was very clear. Thank you.
Thank you.
I think we can move on if there are no further questions from the audience. Okay. We have Mohsen Barzagan is our third and last presenter of this section with numerical, predictive, and experimental study on elastic wave propagation in crystalline rocks. You can start your presentation.
Thank you very much for introduction. So today I would like to present the numerical, predictive, and experimental study on elastic wave propagation in crystalline rock. It's a very big topic. That's why I had to rally a bunch of collaborators to be able to handle. What is the background of this research? It's, we know in a micro scale, we have a different source of anisotropy, like crystallographic preferred orientation, shape preferred orientation, layered of isotropic material, and preferred orientation of microcracks. So to calculate the physical property of this microstructure, we can get a very important information about the rock, because we would see that what is the effect of this microstructure in the bulk physical property of the rock. So to provide the numerical and predictive model and verified with the experiment, it is the background of active research for this area. This presentation is a part of a bigger project, and the objective of this bigger project is numerical or predictive modeling tools are very essential to calculate for the anisotropic materials, because anisotropic materials, they have directional dependency parameters, and to measure all of those parameters in a different directions, currently even in a state-of-art laboratories, it's not possible for the majority of a pressure and temperature condition from the deep Earth crust. So the goal of that big project, which is this presentation is a part of it, is to help us having a better in-depth understanding of a physical property of middle and lower crust or rock. For this work, we used the two deep drilling project samples, KOSK1 and KOSK2 from Sweden, to harvest our samples from them. So the methodology of such a test is started with a laboratory experiment. As we see here, I'm presenting a true triaxial machine. Over here is our sample. The sample is cubic and it will be placed between the 6 pistons. So we're just looking at the plane view of a sample with 2 pistons over here. From the 2 ends of each pistons, we will have a pressure wave and 2 shear waves propagating from one direction and receiving from other direction. By knowing the time of arrival and the distance between the two sender and receivers, we can get the velocity of each sample. Such a machine is capable of increasing the boundary condition pressure and temperature up to 600 megapascal and 750 degrees Celsius. Doing such a test, the experimental test of seismic anisotropy, as we see, it's quite expensive, it's time consuming, and also requires a specific material size that not everybody has that. So we try to use a predictive model to connect seismic anisotropy to the magnetic susceptibility anisotropy. Calculating the magnetic susceptibility is far easier, faster, and cheaper and easier to access with the sample size in the field of geophysics and geology, and it's a very common practice to do that. Therefore, finding a good connection to predict the seismic anisotropy for some specific rocks under under a specific pressure and temperature conditions is very interesting, and it will save a lot of time and money. Then later, here I overly exaggerate the displacement condition of such a numerical model just to present that we have that I place the rock here and I have the two pistons. Over here, I basically send a shear wave. It will propagate through the rock sample and receive from this direction. We test some sample. We take some of our samples to the laboratory, the seismic anisotropy test laboratory, put them under the true triaxial machines, and we test them for the up to 400 megapascal pressure condition and 600 degrees Celsius temperature condition. It was important for us to see the data is correct, is in line with the available literatures, and it basically follow the direction that we predict, so we can use such a data for our modeling verification. When we are increasing the pressure in the top two graphs, we see when we are increasing the pressure, a lot of the micro cracks and open voids are closing. Therefore, density is increasing and the pressure and shear wave velocity are increasing as well. By increasing the temperature boundary condition, the closed cracks are going to reopen again, and the size of the material is expanding. Therefore, we expect to have a shear wave and pressure wave reducing. This data is clearly showing which is in line with the literature data. Because this data is already under review, I just take out the actual rock physics property information of these rocks. So after we run the test and we verified our numerical modeling with the experimental data, what is the sensible next step? The sensible next step are scenarios that we don't have a samples from, but we would like to investigate, such as if we have a layered medium, that the layer formed perpendicular to the wave propagation direction, or if the similar layer formed parallel to the wave propagation direction. What if we are testing a rock with the different grain sizes? Here I'm showing the rock with a very coarse grain is a theoretical rock that only includes 4 grains, and 4 of these grains, all 4 of them are pretty coarse. The next step, I just reduce the size of the grains to look at the compositional effects of the rock on the seismic anisotropy. And the next step, of course, is to see the effect of pore, voids, crack, and later we can easily fill those pores and voids with the viscose material to look at the partial melting. We can fill them up with a different fluid to look at the saturation and effect of the fluid saturation. So what is the benefit of such a research? That's actually a good question to sometimes think about and be critical. So we thought that we came back to the first question again, very beginning of slides, that, okay, the majority of the pressure and temperature boundary conditions in an Earth system are not feasible for us to reach, but there are some that we can reach. So if we can verify our model with those pressure and temperature conditions that we can already run the samples in the laboratory, we can we can basically predict and use the numerical tool for the other condition that is out of the reach for the laboratories at the current stage. The other thing is pure rock physics. Over here, I also, again, overly exaggerate the displacement to show the pressure wave here and 2 shear waves here in 3D in the 6 pistons and the rock placed in between. Because when we are testing our rocks from and we harvest our sample from the core drilled sample, those core drilled, they only giving us one orientation of the rock. We cannot harvest so many samples out of that. But in the numerical modeling, if we have a data from the three principal axes from X, Y, and Z, we can actually numerically orient and reorient our sample and see how does this changing the orientation can affect, like deformation, can affect our seismic anisotropy and seismic data. What is the benefit of that is basically the hope to use those data as a corrected point, just to basically to use as a data point to correct our seismic data, because we know when we are actually measuring underneath the surface, we are going to have so many different layers with a different orientation, with a different anisotropy, and there are so many complications to go and investigate on. So all of this, with regard to the big project, this project has been presented in so many different places. Already 2 of these articles has been published related to the big project, and one of our articles is already, I marked it in blue, is under review from the Tectonophysics. Thank you very much for listening.
Thank you. Thank you. Very nice animations and very clear. So, questions? If there are no questions, I have just a curiosity. I would like to ask you if you are planning, if you're considering the upscaling of these. I've seen that the laboratory examples and are all considering, of course, lab samples that consider a very small scale.
Yeah.
Are you already considering some way to upscale this kind of modeling?
Yes, this image right here is already the upscaled version of the model. So I basically put a corrected data point that I calculated from my numerical modeling in the medium that I created before with the expected geology, but then I corrected within the actual real numerical data, because the values that we have here from the geology core logging, we expect that the velocity of material right here, like a gneiss or amphibolite or granite, could be this pressure or shear velocity. But when we are going from the surface to depth, the pressure and temperature conditions will affect that rock over there, and therefore it will change our understanding of what is the wave propagation velocity over there. So I try to upscale it over here. So basically using of this point is to using this numerical tool in the laboratory is to select and prepare a lot of data points that you later can use in your seismic interpretation for correction of what do you think do you have underneath the surface.
All right, thanks.
You're welcome.
We had someone with their hand up. Never mind.
Sorry, was that a question?
Someone had their hand up, but now they took it down. So I guess we're good.
Yeah, maybe I
right.
just widely. Yeah.
Okay, we can move to the second session. And I'll pass the word to the co-chairs.
Is it maybe best to have a 5-minute break first then? Because we're running ahead of schedule. Roberto, I don't know what you want to do.
Oh, right. Yes, yes. Let's have 5 minutes of break and we'll just start from there.
Yeah, because it's 10 minutes officially to the next presentation, right?
Today my talk is about the importance of characterizing overburden rocks in a CO2 storage site. So in our case, it's Aurora, a storage site located in northern North Sea. This project is already approved by the Norwegian government and under the name of Longship CCS project. So what is CCS means and why overburden is important? So CCS means carbon capture and storage into subsurface. So for example, if you see in this picture, this is taken from Equinor webpage. So the concept is capture CO2 from industry and then transported to a reception plant. And then from there, those CO2 inject into a rock underground 2 to 3 kilometers below the seabed for a secure storage. So this whole process is called CO2. But just think about it. If we inject something into a confined aquifer, there might be some consequences. For example, maybe capped rock shear fracturing could occur, or possibility of reactivated the faults. So we have maybe leakage. So in that scenario, CO2 plume will migrate upward into the overburden. That's why overburden characterization is very important. So next couple of slides, I'll show you my study area and objective, and also which data and methodology we used. And instead of result, I would say this is a preliminary observation, because this is very initial stage of this work, as well as this is also qualitative work. And based on that, I will conclude. So study area, if you see in this map, so this is mainland Norway, and this part is Norwegian North Sea, and this is Norwegian Sea, and this is Barents Sea. So our study area is located northern North Sea, as I said earlier. So this is the zoomed section, and I think most of you hear about Troll gas field. So Troll gas field is located there, Troll East and Troll West. And few major faults such as Thuse fault, Esvarta fault, and Troll fault. These are major faults are also located in that area. These other lines are also faults. Those are minor faults. So our study area Aurora is located just south of Troll West field. So Aurora is located here, and you can see in this well 3157. This well is recently drilled, and this could be a future CO2 injector. So this oil is also located there. However, north of Thuse fault, so somewhere here, we found a gas chimney effect. So this is Thuse fault, or this is the section from A to B here. So you see this Troll gas is located somewhere here, and we found this high amplitude within the overburden. So this is one reason we want to evaluate rock overburden fractures and fault pattern and intensity to identify the possible risk we have when we will inject CO2 in this area. So that is the objective. Also, we use this gas chimney effect as the analog to evaluate Aurora area. So we have a 3D post-stack seismic named GN10M1. So I use this 3D post-stack seismic and generate variance cube using Petrel 3D attributes module. And you can see here, this seismic section is actually A to B. And for your reference, this is that gas chimney effect with Thuse fault. So I choose two overburden surfaces above and two below. So top Shetland, top Rogaland, top Woodland clay, and top CAD. So I interpreted these horizons and I generated the time surfaces. So when my 3D variance cube is ready, I just extract variance properties on top of that surface using surface attribute function. Also, you can see this is our well, injector well. So we will inject CO2 in this region. So this top Jonsen or Jonsen formation is the main reservoir in this area, or the targeted reservoir, and top Drake formation is the main cap rock. So you see this bed is dipping towards south. So if we inject CO2, the possible plume migration would be in this direction, and the northern direction. So this Esvarta fault can play a vital role. So it's very important to evaluate that Esvarta fault to evaluate the possible risk. Also, this attributes, variance attributes, actually gives us the horizontal discontinuity. So whenever we have continuous horizons, then there would be very low amplitude, variance amplitude. But whenever we have some discontinuity, such as faults or fracture, we're gonna have a high amplitude, and that represent faults and fracture. For example, here, if you see, if we have like this grayish color, scale is 0 to 1. This gray color means like there is no faults or fracture present. But if we have like blackish, reddish, or yellowish, this zone, or you can see these lines. So this indicate we have faults or fracture in that zone. So here you can see first two surface, top Shetland and top Rogaland. Also, for your example, for your reference, this is that troll east and west polygon is also here, and this location is the gas chimney we found, and our injector is located here, 3157. So in Shetland, we see like all the major faults. You see these lines. So all the major fault traces are visible here. Also, this is that important Esvarta fault trace is also located here. But just top of Shetland, top Rogaland. So in this section, you see top Rogaland. We are expecting this Thuse fault trace here. So actually, Thuse fault is visible here, because a gas chimney is located on top of this Rogaland group. So yeah, as expected, Thuse fault trace is also seen here. But good thing is that this Esvarta fault is almost die out within this top Shetland and top Rogaland group. And we check this upper two formation, top Hordaland clay and top Scat. So this is top Hordaland clay, and we are not expecting this Thuse fault up to here. So there is no trace of Thuse fault. Actually, no major faults present in this level. But however, you can see these colors, this fracture and a small faults pattern significantly high in this injected area compared to like where we have this gas chimney effect. Similar thing also observed in top Scat, but the intensity is little bit less, but significantly higher than the area where we have that gas chimney effect. And we are expecting less faults or fracture in this area, because you can see here, we found that accumulation is stopped somewhere in between. So we shouldn't expect much fault and fracture in this area. So based on our observation, we suggest like it's less likely to have a fault parallel flow, because this Esvarta fault is die out within in between Rogaland and Shetland group. However, if that fault parallel flow happened here, that consequences will be significant, because of this significantly high faults and fracture in this area. So that's based on our analysis, we actually recommend a detailed overwater characterization, which actually I already started, to prevent any unwanted incident in future when we really will inject CO2 into that area, in Aurora area, somewhere here. Yeah, that's in my presentation. Thank you everyone. If you have any question.
Yes, thank you very much, Yamilur. It was a very interesting presentation. I think we do have questions from some of the panelists. One of them is saying perfect presentations, thanks to the presenter, so compliment to you. And Jean-Marc, I think it's the name, is asking how induced earthquake by CO2 injection are mitigated for such project.
Can you?
Yes, if you want, you can read also from the chat, but it's how induced earthquakes by CO2 injection are mitigated for such project.
Okay, so we are expecting induced seismicity, but it depends on how much injection pressure as well as the volume. So I'm now working on geomechanical modeling. So we will actually identify the optimal injection rate and injection volume so that we don't have any fracture within our caprock. Okay? Or like you've seen, like we have those major faults. So we have a risk of fault parallel flow or reactivation of those faults. So using that geomechanical modeling coupled with fluid flow, we can answer a few of those questions. So I started that work already, and hopefully within 3-4 months later, I have some answer. Yeah.
Great, thank you. And we have a comment from Mohammed that says, I like the idea and the interpretation of model, especially the locating of the faults. Yes, and again, for the audience and also for the panelists, if you have more questions, you can place it in the Q&A. We do have another question from Karim that says, can you clarify the overburden significance, I guess, in the CCS?
Yeah, so for example, if you, so this event, so this hydrocarbon is fault parallel flow, or we used to call gas chimney. This is from the Troll field. The Troll reservoir is located somewhere here. So this actually motivates us to do an analysis, like if something happens similar like this one, because we have to say a Svarta fault also located here. So is our overburden is capable in this area, is overburden is capable of holding like this overburden can do. So actually this surface, I actually interpreted this one as well, and it's end up here. So we don't have actually this maybe soft clay type material which hold this hydrocarbon here instead of going back to the surface or in the seafloor. So with this layer, this horizon is actually kind of pinch out somewhere here. So we don't have that layer here, and that's also indicate, you know, too many faults and fracture in this region compared to in this in the eastern side. So that's another issue. So we are thinking like, well, maybe because of this Svarta fault is die out in this zone, so we have less chance. But if something happen, then this area is much highly fractured and faulted compared to this area. So there are less chance of, you know, like what we are seeing here, like accumulated here. If something happened, it will actually come to upward, and if we have some soft clay here, maybe accumulated there, otherwise it will come back to the seafloor, what we don't want. Okay. So that's why we need to evaluate overburden as well as during geomechanical model. So if we are talking about injecting pressure, will introduce expansion of our rock, so that will expand our overburden as well. So we need overburden, rock properties, rock strength, for example, Young's modulus Poisson's ratio for overburden as well. So normally we only focus on reservoir and caprock, but overburden is also very important. So we actually have seismic inverted, pre-stack seismic inverted rock strength properties for overburden as well. So in my geomechanical modeling, I will use the seismic generated properties which can cover overburden section as well. So yeah, that's why overburden is really important, which is neglected most of the time, you know, in oil or gas industry.
Yes.
Okay, thank you. I have one more question here I see from Farida. He says, thanks for the interesting study. Do you have any analysis of the sealing capacity of the minor faults close to?
Oh, well, so minor faults, for example, you can see here, we have many minor faults here, and we don't find, we have this giant troll field in this area, And these minor faults here, for example, it's sealed. So we have confidence like these minor faults are sealed, and displacement is very little, but it's like more of a fracture than faults, though it's faults, yeah, very small displacement. But our confidence is like because of it's sealing for troll gas field, so it's sealing for our CO2 injection as well. Yeah, but definitely we will add few minor faults in my geomechanical model as well with major faults. For example, this fault, this is very important for our geomechanical modeling because maybe this will act as a barrier, so that may have issues on our volume, overall volume. So yeah, I will add some minor fault as well. Thank you.
I think that we are now close to the next presentation. So thank you for your presentation again, Emilio. And our next presentation will be by Marleen Lunde from Bergen University. And she's going to talk about constraining carbon turnover in Arctic and subarctic sediments using pore water carbon isotopes.
Okay, hello everyone. Can you hear me?
Yes.
Yeah, super. Okay, so as I said, my name is Marleen, and I'm doing a master at the University of Bergen. My master is called Constraining Carbon Turnover in Arctic and Subarctic Sediments using pore water carbon isotopes. And my co-authors and my supervisors are listed on this slide. So first off, I want to start by telling you a little bit about the carbon cycle. So it involves many processes, but I'm mainly going to focus on the stuff happening in the ocean and especially in the sediments. So CO2 from the atmosphere dissolve in the surface water, then photosynthesis in organisms turn the carbon into organic matter. Then when the organism dies, it sinks to the deep, and some of the organic matter is being decayed, releasing CO2 into the ocean again, while some of the organic matter is arriving at the sediments where it gets respired or it gets trapped in the sediments. So that's the focus of this study. So in order to investigate the carbon in the sediments, we use something called the delta C13. So the delta C13 is just a relationship between the light isotope C13 and the heavier isotope C12. So the delta C13 in seawater is approximately 0 per mil, while the delta C13 in organic matter is approximately minus 25 per mil. So that means when we add organic matter or we respire organic matter, the delta C13 drops. So my main supervisor went to the Barents Sea in 2018, and he collected pore water from sediments outside of Svalbard. And he looked at the delta C13 in the pore water. So the main idea is that oxygen controls the organic matter decay in sediments in the upper part. So here you can see on the right side, two stations with the same bottom water oxygen concentration, but you can see they have both very different respiration profiles. So one of them is respiring more organic matter than the other, even though it has the same amount of oxygen. So then it's hard to reconcile that it's only bottom water that controls the delta C13 change in these profiles. So then we raised a couple of questions that I'm going to try and answer with my master. So we wanted to see if this pattern is typical for other places. And we want to see what role does the oxygen play and what other controlling factors is there. Is it common to shelf areas, to high latitudes, or it's only unique to the Arctic glaciated shelves? And ultimately, this raises a very important question. Do the delta C13 can the delta C13 be used as an oxygen proxy, or does it even make sense? So I went on a cruise in 2020 called the Cyan Cruise, and I took some sediment cores from different places. So we took gravity core, multi-core, and box core, and we extracted water from the sediments called pore water. And we also did some CTD so that we could collect bottom water at the different stations and also look at the oxygen content in the bottom water. So we went from Bergen along the Norwegian coast up to Svalbard, and then we went over to Greenland, down to Iceland, and then back to Bergen. So the results from the analysis you can see on the left side. So the delta C13 in all the stations starts at a value of around 0 to 1, and then all of them decreases as we go down core. But some of them are decreasing more than others. So is there a pattern? So here on the left side, you can see a lot of stations, and I have listed them with the station with the lowest delta C13 in the upper part of the list, and then station 10 with the highest delta C13 in the end. So you can see that it's also somehow listed from the shallowest station to the deepest station with some outliers. So apparently there is some connection between the water depths of the different sites and the delta C13 that we observed at 10 centimeters. So we wanted to see if this was the case also with the oxygen. So we found the oxygen penetration depth by doing measurements of oxygen in the sample. So that means that I have listed the depths at which the oxygen is assumed to be gone. So at station 1, for example, the oxygen is gone by 0.5 centimeters, while for station 7, which is very deep, it's gone by 5 centimeters. So this is likely related to the amount of organic matter being added to the seafloor. So how much flux there is of organic matter from the sea surface to the sea floor. So in the case where it's shallow water depths, more of the organic matter reach the sediments because less of it is being respired in the water column. So is this common to certain areas like shelf areas and so on? So here I have a map over the different stations, and I also have colored them. So the green ones are the ones with the lowest delta C13. So they are the station with the most organic matter being respired, while the red ones are the ones with less. So it's at the highest delta C13. So you can see like all of the green stations are situated on the east side of my study area, while the other ones are on the west side. And you can also see, for example, station 12, which is approximately 700 meters, and station 3, which is also the same water depths. They have different values. So the one on the east side has a more negative delta C13 than the one on the west side. So it seems like there's some difference between the geographical situation of the station as well. So then we wanted to investigate if there is more carbon being added in the stations on the east side. And from a plot from NASA, you can see that the primary production of carbon per square meter per year is actually more in the Norwegian part of my study area compared to the Greenland coast. So then we want to investigate if a carbon delta C13 is a good proxy for oxygen. So we did measure the oxygen in the samples, right? So that's the green line in these graphs. And we also did use the delta C13 and we calculated how much oxygen would change down core with the delta C13 change. So as you can see, that's the orange line. And they fall kind of perfectly together. You can see the delta C13 and all of the lines falling perfect together. So we measured oxygen to be gone at approximately 2 centimeters in station 5. So you can also see that the calculated oxygen, the ones that we used the proxy on, also say that oxygen should be gone by 2 centimeters. So in this case, it actually works to use delta C13. While in station 10, you can see the lines are not as perfectly together. And we measured the oxygen to be gone by 4.5 centimeters, while the calculations say that there should be oxygen present all the way down to 23 centimeters in the sediments, which was not the case. So in this case, it's not a good proxy to use. So just a very quick summary. So the delta C13 that we measured and the oxygen that we measured decreased faster in shallow stations. The oxygen is also mainly responsible for the changes in only the upper around 4 to 5 centimeters. We also see that the oxygen and the delta C13 is not perfectly coupled, and that the use of delta C13 as an oxygen proxy is not as good in all stations. We also see that the Greenland margin, which is glaciated, is not similar to the Barents Sea and not similar to the Norwegian Sea. And organic matter availability seems to be more important than the amount of oxygen when it comes to the decay of carbon in these stations. So the next step of my master thesis, or the next step in this kind of study, is to use nutrients like iron, manganese, and also to find the total organic carbon to quantify other processes that can contribute to these delta C13 changes. And that's what I have. So thank you for listening, everyone.
Thank you, Malin. Are there any questions? Doesn't seem like it. I'm not very familiar with this topic, so it's maybe sometimes hard to understand everything that you were talking about. Could you maybe, for me, as basically someone that doesn't know anything about this, have a little bit more in-depth detail of how you perform all these different tests? How do you measure these different values?
Yeah. Okay, so as I said, the lower the delta C13, like the lower you go, like more to the minus side, the more organic matter is being respired, because the signature of organic matter is minus 25 per mil, right? So there's a proxy of oxygen that we use. So many people use the amount of delta C13 to reproduce earlier oxygen levels. So in our case, we have looked at the oxygen and seen how the oxygen is decreasing down core, and also seen how the delta C13 is changing down core. And in many of the cases, the amount of oxygen available do not support the change of delta C13. So even though oxygen is gone, the delta C13 keeps on decreasing. So in theory, it should not do that, but it does. So that's why we're testing the theory of using delta C13 as an oxygen proxy. And in some cases, it actually do work, but in some cases, it do not work. So it's just that these measurements that we have are not like the normal case earlier. So it's more lower than it is expected to be. And we want to investigate if it's on other electron acceptors doing it. So okay, yeah, and we do this by taking pore water from the sediments, and then we put it in a delta ray machine. So the delta ray then can measure the delta C13 in the sample.
And is this project, is this unique to like this part of the world, or do you know of other places in the world where they have done conducted similar studies?
I think it's a pretty new. It's new to people. So when they went in 2018 and they found this very negatively delta C13, they were very surprised. So that's why I did like a bigger cruise to see if this was actually applying to other places, because in 2018 they visited like the northern part of Svalbard, like in the Barents Sea. So it's not as negative as in the Barents Sea, but it's still more negative than, for example, other places. So I don't know if they have seen these type of values in other places. I don't think so.
Okay, thank you. I see there are coming in some more questions now, so that's good as well. Farida asks, what are possible applications of these findings for the industry?
I think it's more just to understand the carbon cycle, like what's happening in the sediments in the Arctic. So I don't know how they can use this in the industry, but it's more to understand what's actually happening.
Okay, yes, thank you.
And we also have, yes, a question in the chat from Ross. And he's asking, how do you foresee the melting of the northern hemisphere ice sheets and the consequent changes to depth to deep water circulation in the ocean is affecting these carbon isotope ratios at the seafloor?
Okay, so first we assumed that we would see these very negative values around the Arctic shelves because of meltwater from the glaciers. So when the meltwater, it contributes to more electron acceptors so that they can turn over the carbon so it gets lighter. So we were actually expecting to see lower values around places where there is more glaciers, for example, around the Greenland coast, but we do not see that. So I'm actually not sure yet because it's so new still. And yeah, we need to do more science on this part.
All right, interesting. Thank you, Malin. Robert?
Sorry, I think there is a raised hand from Mohammed Chad as well.
Good morning. Yeah. Good morning. So I'm sorry, I have tried to catch up. I did catch up something from your presentation, but can you please give me the main idea exactly? What's about exactly in terms of practically, I mean practically. Thank you very much.
Okay, so just summarize what I just told you. Summarize the presentation.
I guess.
I mean in terms of your research, practically. I mean, okay. Thank you very much.
Okay. So I have been taking pore waters from different stations around the Nordic Sea, and I have been investigating the carbon isotopes in the pore water in the sediments. And we found out that the pore waters in the sediments have much lower delta C13 values than we were expecting, and they are decreasing even though oxygen is gone. So we don't know if we don't think that the delta C13 can be used in the oxygen proxy. So that's mainly what I'm studying to see, and see what other electron acceptor is contributing to these changes. So I actually got some nutrients today, so I'm going to look into that now or after this presentation.
Perfect. I get it. Thank you very much.
No problem.
Yes, thank you, Malin, for a nice presentation. And then I think I will hand over to the. Well, first let's make one more remark. Please, if you have any questions, try to ask them in the Q&A section. So you have a chat option and you have a Q&A option at the bottom of your Zoom screen. So please use the Q&A option, then it's easier for us to find and locate your questions and ask them to the speakers. And then I think I can hand over now to the third session. So Anna and Turan will host you there.
Yeah, thanks, Yona. So I think for now we're going to have 5 minutes break till the third session, and then we'll start with Deborah Wenner from University of Cambridge.
On case studies, and we start with Deborah Wiener from University of Cambridge, and the title of her presentation is Deciphering Southeast Asia's Tectonics: An Introduction to Full Wave Inversion in Seismology.
Perfect, thank you very much. Can you hear me, and are my slides showing up?
Yes.
Perfect, thanks. Well, thank you very much for joining. Today I'd like to present some intermediate results from a PhD project which focuses on full waveform inversion beneath continental scale Southeast Asia, as shown here. Full waveform inversion, or FWI, has become a buzzword in the petroleum industry, but seems poorly understood outside a small group of people. So I'd first like to talk you through the motivation and the background of FWI in earthquake seismology. That is, we're using earthquakes as passive seismic sources to image the subsurface down to several tens or hundreds of kilometers. However, the concept is very similar to FWI in the exploration context. And then I'll continue with the application to Southeast Asia. So the majority of tomographic studies are by far ray-based travel time tomographies, with their first applications in the 1970s. And as illustrated in this figure, these traditional tomographic methods are based on picking travel times for different phases that travel through different parts of the Earth, and hence arrive at different times at a station. So here we're looking at arrival times of body wave phases, which travel through the Earth's interior, while the later part of the seismogram shows large amplitude surface waves, which are confined near the surface. And these ray tomographic methods are computationally cheap, and we can include vast amounts of data, but besides the arrival times, the rest of the seismogram is ignored. The other problem lies in the theory. These methods are based on an infinite frequency approximation, assuming seismic waves travel along rays connecting sources and receivers as shown here. But it's long been known that seismic waves are sensitive to a volumetric, an extensive volumetric region outside of the geometric ray path. So we can overcome the limitations of ray theory by computing the 3D seismic wave field numerically. And on the right, I've visualized the wave field for magnitude 6.9 earthquake that occurred south of Indonesia. But the computation of the 3D wave field makes the method computationally expensive, but it allows us to embrace the full complexity of seismic wave propagation, accounting for the effects of anisotropy, anelasticity, wavefront healing, and interference, and it allows us to incorporate all information in a seismogram coherently. The method originates in seismic exploration and has also been successfully applied in other areas such as medicine and engineering. So how does full waveform inversion work? The method is tied to a tangled complex workflow, so we're just going to skip through it today. FWI is a gradient-based iterative optimization scheme where an initial model is updated based on the difference between synthetic and observed waveforms. So we start off with obtaining synthetic seismograms by simulating the 3D wave field, thereby taking into account both body and surface waves. The obtained synthetics are compared to observed waveforms, making use of the information of, in theory, the entire seismograms. And the difference is summarized in a misfit represented by the gray area here. To minimize the misfit, it's gradient is computed, and the gradient tells us in which direction the misfit decreases, and it can be seen as a generalization of the wave path. So it represents the volumetric area that seismic waves have seen when traveling through the Earth. And here I've visualized this for a single source receiver pair, but our actual gradient during the inversion is made up of the sum of all possible source receiver combinations. And this tells us which parts of the model we should update in order to decrease the misfit between the waveforms. The model is then updated using a gradient-based optimization scheme, such as conjugate gradient or LBFGS, and this process is iterated until some predefined criterion is fulfilled. Or, to cut a long story short, we go from this to this, and spoiler alert, this is actually one of the Indonesian stations I'm using. So let's move on to the application to Southeast Asia. Southeast Asia is one of the least well understood areas, as it is one of the most complex tectonic regions on Earth, and this is mainly a result of its location within the tectonic triple junction of the Australian, the Eurasian, and the Philippine sea plates. And most seismicity occurs along these highly active tectonic plate boundaries, all moving a few centimeters per year. And here I'm showing all earthquakes with a magnitude larger than 5.5, colored by depth. So in the West, large magnitude earthquakes are generated by the Australian plate subducting beneath Indonesia. And in the East, we observe deep events with depths of up to 700 kilometers indicated by the dark colors, and a complex configuration of minor tectonic plates. I'm plotting Bird's plate boundaries here, but there is no definite answer as to the number of tectonic plates and where their boundaries lie. So overall, the area is an ideal target to investigate different phases of the tectonic subduction cycles, such as ongoing subduction along Indonesia, as well as two post-subduction settings around northern Borneo, that is, subduction stopped there a few million years ago. Thus, my project aims to obtain a new large-scale image of the entire region to understand Southeast Asia as a whole, and full waveform inversion is particularly suitable for imaging such complex parts. Realistic synthetics are obtained using the spectral element solver-salvus, accounting for anisotropy, attenuation, topography, and bathymetry, and we are approximating the fluid ocean by the weight of its water column. There exists a whole zoo of ways to quantify the difference between observed and synthetic waveforms, but we're using a time and frequency dependent phase misfit, which makes use of the phase and relative amplitude information of a seismogram. We're selecting suitable portions of the seismogram as shown in gray here, using a data selection algorithm called FlexWin, and this allows us to specifically account for body wave signals by selecting a separate window around them. Again, these are the P and S waves that travel through the Earth, so this allows us to maximize sensitivity to deep structure. The difference between observed and synthetic seismograms is summarized in the MISFIT, combining the signal of many different sources and receivers. And here I'm showing the normalized MISFIT for the first 70 iterations across 6 period bands. So we're starting off at 100 seconds and then go down to 80, 65, 50, 40, and ultimately 30 seconds. Each dot here represents a model update, and you can see how the MISFIT decreases within each period band. And once the MISFIT stagnates or we've run enough iterations, we decrease the smoothing length or go to shorter periods. You may notice that we consider relatively long periods here. So in the exploration context, you usually look at several hertz rather than tens of seconds. And this is because our study area is much larger and it's computationally too expensive to sample the wave field more frequently. Still, so far we've already burned 26,000 CPU hours and generated several hundreds of terabytes of temporary data. So this is mostly running on the Cambridge High Performance Computing Cluster. The MISFIT decrease I was just showing is entirely driven by a waveform match improvement. Here I'm showing the waveform comparison across 4 of the 6 period bands for a single station receiver pair. We're looking at the Z component for a station near Bali, which recorded a magnitude 6.2 event south of the Philippines. For each period band, the final synthetics, represented by the solid reddish line, matched the black observed waveforms better than the synthetics from the initial iteration within this period band, represented by the red dashed lines. We're seeing strong initial delays in observed waveforms with a particularly large time shift at 100 seconds, indicating that our starting model was way too fast. From 65 seconds onwards, the waveform match is already excellent. And from 50 seconds onwards, 2 windows are selected, one around the smaller amplitude body wave and one around the larger magnitude surface wave arrival. Looking at the bottom figures here, one could ask, is it actually necessary to slowly blend in the shorter periods? Can't we spare some computational resources by looking at shorter periods right away? So let's zoom in on the final period band at 30 seconds. We're now looking at a waveform comparison of observed data, synthetics of our final iteration at 30 seconds, and you can see that our model is able to explain the observed waveforms very well. And the dashed line shows synthetics of the starting model at iteration 0. So we're essentially looking at the waveform match if we would have started off at 30 seconds right away, noting that we're using a one-dimensional starting model since there's no region-specific model available. And our starting model is able to explain the first arrival reasonably well, but the match is insufficient for the later part of the seismogram. And this emphasizes the importance of this multi-scale approach, that is, starting off at longer periods. We wouldn't be able to define a meaningful waveform difference for the initial and observed waveforms at these periods without running the previous iterations at longer periods. There are some more reasons for why we have to adopt a multi-scale approach, but this would be beyond the scope of a 10-minute talk. Now let's move on to the model itself. The most prominent features are the Sunda and the Banda slab, that is the Australian plate subducting beneath Indonesia, which is indicated by the fast velocities represented by the blue colors here. And I'm here showing how these features build up across the different period bands for a shear wave depth size at 200 kilometers. So they first appear at 50 seconds and then become sharper as we decrease the period. On the right, we're seeing a cross-section in the west of Borneo, so we're just cutting through our model along this line here. And we're looking at it from the side, and you can see how the shear wave variations with depth. And this reveals that the Sunda slab extends down to the mantle transition zone, but we do expect some more detail to appear in our 20-second simulations, which are currently running as we speak. So what I would like you to take home today is that full waveform inversion is computationally very expensive, but it promises higher resolution images as it overcomes the limitations of traditional tomographic approaches. And it is an especially suitable imaging method for complex parts of the Earth, as it can account for full wave effects, which can hamper other seismological methods. Here we're presenting the first continental scale 3D seismic structural model beneath Southeast Asia, obtained from full waveform inversion, imaging subsurface structures down to 500, 600 kilometers, including multiple subduction zones, such as the Australian plate subducting beneath Indonesia. We're currently running the final iterations at 20 seconds and then we'll assess the robustness of our model. However, resolution tests and for waveform inversion are generally considered an open research question, since uncertainty quantification is currently prohibitively expensive to obtain, but there are some data-driven approaches that we're currently investigating. So this research is supported by the EPSRC, BP, and Schlumberger, and I think I'll leave it here and I'm happy to take any questions.
Thank you, Deborah, for your presentation. Any questions from the audience? We have one question from Mohamed Jed. Oh, it's not a question. It's a compliment. Thank you very much for your practical conclusion. Okay.
You're welcome.
So any questions from anyone? Well, I have a question. I think it's a really silly question, but how do you acquire the real data, the real seismic data?
Yeah, so since we're using passive sources, we're not really going out like you do in exploration and like fire air guns or anything. So we're just deploying seismometers in the field that measure continuously for at least a couple of months, usually a couple of years. Yeah, so they're around, I have access to, I think it's 440 stations deployed within Southeast Asia that have been recording earthquakes over the past 5 to 20 years.
Okay, thank you. So there's any questions? Well, I don't think so. Thank you very much, Deborah. We have one, sorry.
Okay.
From John Mark. You can ask your question.
Thank you, Deborah, for the presentation. I have a question about the component. I saw for one slide that you use the set component. Did you have an idea about the E or N component, how the behaviors was it?
Yeah, that's a really good question. So usually the Z component is less noisier because it records so it's the depth component, so it usually records the waves that come in from the bottom, whereas the horizontal components, the easting and northing, tend to be noisier, but I'm still using them. So I think during my inversion, it's usually 30 to 40% are horizontal components and 60-70% are depth component seismograms, because they record the surface waves more strongly, but we're still using them. I just don't have an example here to show you. Sorry for that.
Thank you.
Okay. We can move on. Well, there is a question. We have another question from Karin Cherozana. And how you evaluate the synthetics model FWI? Sorry.
I'm not quite sure if I'm understanding the question correctly. Do you mean how do we evaluate our final model that we have obtained? So these are the kind of resolution tests or robustness tests, or do you mean how we're picking our starting model, our initial model?
Well, I think the question is the initial model.
Yeah. Okay. Yeah, so that's quite tricky. It depends on the region you're working on. So if you're lucky, there's already a region-specific model available, maybe from ray tomographic studies. So you could just smooth that out and then start off with that. That wasn't really the case for Southeast Asia because not much work has been done there, at least not on this scale. So that's one of the reasons why I'm starting off at this really long periods of 100 seconds. Where our seismic waves are essentially just seeing the overall continental scale structure. And I can start off with a one-dimensional model. So I'm using essentially a modified version of PREM here.
Okay, thank you. Any more questions? Okay, now I think we can move on. Thank you, Deborah. And I'm going to give my word to Turan.
Thank you, Deborah, for such a great presentation. So now we're moving to our second presenter in our third session. That would be by Mohammed Awais from the University of Nepal's Federico II, with his topic Outcrop Scale Reservoir Studies and Petrophysical Log-Based Lithology Interpretation, a case study of Neothesis Eocene rock unit. Thank you.
So thank you, Thoran. Can you see my presentation?
Yeah.
Okay, fine. So
Can you open it just to see?
You need to put it in presentation mode.
Yeah, it is in a presentation mode.
Then you need to.
Wait a minute.
You need to share it. Yeah.
Is it fine now?
Yes.
Yeah.
Okay. So I am Mohammed Awais, PhD student in Department of Earth, Environmental and Resource Sciences, University of Naples, Federico II. The topic
no, we can see your notes again. We can see your notes again.
Okay, sorry. Now it is fine?
For now, yes.
Yeah.
Okay. So the topic of my presentation is Outcrop Scale Reservoir Studies and Petrophysical Logs-Based Lithology Interpretation, a case study of Neothesis Eocene rock unit. So the contents of presentation includes introduction, tectonics and stratigraphy, materials and methods, lithological studies using the outcrop data and geophysical log, followed by reservoir characterization and conclusions. So introduction into the study area. The present study area belongs to salt range and Potawar Plateau, which are parts of the northwestern Himalayan fold and thrust belt. And Potawar Plateau is the former oil-producing province of Pakistan, where the first commercial discovery was made in 1914. And the major hydrocarbon reservoir rocks are Paleocene and Eocene carbonate rocks. The Eocene carbonate succession includes the Namal Formation, Sakesar limestone, Margala Hill limestone, and Chorgali Formation. So Chorgali Formation is the subject of present study, and generally it can be considered as a Neothesis Eocene rock unit, and it is in the mentioned Eocene succession. It is the youngest unit, and it is one of the most important Eocene rock units with hydrocarbon potential in the salt range and Potawar Plateau, and it is a significant oil producer in different oil and gas fields. For example, Dakhni, Torqual, Satkal, Simkasar, Balsedan, and Misakeswal. Tectonics and structural framework. So the geological map to the left shows the position of the Potawar Plateau. So this is the Potawar Plateau, and below we have over here in the form of a band, this is the salt range, and the studied outcrop sections together with the studied wells, they are marked on the geological map in the form of colored stars. And to the right, we have a seismic section which belongs to the oil field whose well data has been used, and it is showing us a pop-up structure and implying that the area is dominated by compressional tectonic regime. Stratigraphy, the present study area belongs to Heremurat range, which is part of Potawar Plateau, Mial oil field, and the salt range. So to the left, we have the outcrop stratigraphy of the Heremurat range, which consists of Eocene and Miocene succession. In the middle, we have the stratigraphy of the subsurface Mial oil field, which ranges from Permian to the Pliocene succession, and to the extreme right we have the generalized stratigraphy of salt range and Potawar Plateau, which ranges from the Precambrian salt range formation to the recent sediment, and the present target formation in each of the stratigraphic section is marked by red color stars. Materials and methods. The present study consists of surface outcrop data and subsurface well data. A fieldwork has been conducted to the Potawar Plateau and the salt range, which is then followed by laboratory analysis. Reservoir characterization on the outcrop scale are conducted, followed by fracture study under the microscope, and plug porosity and permeability analysis are also conducted. And the subsurface well data consists of open hole logs of 3 wells, well number 1, well number 2, and well number 3, and the gamma ray log and the combined neutron density log and the cross plots of neutron and density logs are used for the interpretation of lithology. Now, lithological studies of the Chorgali formation using outcrop data. 6 outcrop sections have been studied, including Gali Jagir School section, Gali Jagir Dam site, Chua Sedan Shah, Karoli, New Lawahan, Nala, and Versanal. And the overall generalized lithology of the Chorguli formation is a mix of carbonates and plastics. So on the outcrop, it is dominantly a carbonate consisting of limestone and dolostone with minor sandy limestone, evaporite, calcareous sandstone, marl, conglomerate, and shale intercalations. Now, field photographs of the Chorguli formation. So the photograph to the upper right, it belongs to the Gully-Jagir dam site section, and the rest of the photograph, belongs to the Gully-Jagir school section. So both of the sections are folded, and similarly, there is also intraformational fault in the lower left corner, and followed by a black colored diagram, which is actually algal laminations and contains gypsum and dolomite. And in the extreme right corner to lower right corner, we have the thick bedded dolostone. Now, field photographs of the Chorguli formation at Chua Sedan Cha section. So in each of these diagrams, above this blue and the green line, this part of the outcrop, it is actually a Chorguli formation. And at the Karoli section, so above this blue diagram to the left, we have this outcrop which is quite poorly exposed. It is a Chorguli formation, and over here in the right part, we have intercalations of shale in the massive limestone unit, which is also a same Chorguli formation. This is another section, which is the Versanal section. It consists of medium to thick bedded limestones with some shale, and at places nodular limestones have also been found. Now, this is another section, Nilavahan Nala section. It is comparatively more close to the clastic sedimentation. So over here in the upper left, we have a diagram which shows the contact between the Sakesar limestone and the Chorguli formation. So the geological hammer is at the contact of the formation. In the lower, we have the Marley unit, and in the middle, we have the Marley sandstone, and in the right, we have the conglomeratic unit of the same formation, and in the lower right, we have the Marley unit. Now, stratigraphic columns of the Chorguli formation at different sections. So in the left, we have the stratigraphic column of Gully-Jagir school section, and it has a thickness of 62 meters. And in the right, we have the Gully-Jagir dam site section with a thickness of approximately 28 meters. In the left, we have a Chua Sedan Cha section with a thickness of approximately 8 meters, and in the right, we have a Versanal section with a thickness of approximately 6 meters. In the left, we have a Karoli section which has a thickness of 4 to 5 meters, and in the right, we have a Nilavahan Nala section which has a thickness of 17 meters. Now, lithological studies of the Chorguli formation using geophysical logs. So, three types of open hole logs have been used, dominantly gamma ray log and the combination of neutron and density log. So 50 API is considered as a shale baseline, and anything above the 50 API is considered as a shale lithology, and anything below is considered as a reservoir lithology, or at least the non-shale lithology. And then the reservoir lithologies are further divided using the combination of neutron and density logs using a technique of Lucia 2007. So wherever the neutron density logs overlay, it is considered as a limestone, and wherever there is a separation between the neutron and density logs, provided the gamma ray log is below the 50 API, it is considered as a dolostone. And likewise, using the photoelectric effect log and the density, some of the evaporites have also been identified, and all of these three wells, they are dominated by dolostone with minor limestone in shale and with some evaporites at different stratigraphic levels. Lithological studies of the Chorguli formation using cross plot of NPHI and bulk density log. So for these three wells, such cross plots have been constructed, and wherever there is the clustering of points, so that lithology has been considered as the dominant lithology. For example, dolomite in this case, and then found in association with some minor limestone, shale, and anhydrite. Reservoir characterization of the Chorguli formation. So for the reservoir characterization, plug porosity and permeability analysis have been conducted, and the porosity varies from 1.8 to 2.9, and the permeability varies from 0.064 to 2.2 millidarcy. And on the outcrop scale, fracture analysis have been conducted using the skein line survey. So the overall length of the skein line over here, you can see it is 250 centimeters, and the cumulative fracture interval is 216 centimeters. Therefore, it is implying extension and opening, which ultimately leads to the porosity and permeability. And most of these fractures, these are the conjugate fractures, and dominantly they are striking in the northeast direction. Then one of the section of the Chorguli formation, the Koroli section, it has been intensely fractured, and there is some kind of mesh of fractures. And under the microscope, 3 episodes of fracturing have been interpreted, and these photomicrographs, they belong to the Galijagir school section. And based on the cross-cutting relationship, these fracture episodes have been interpreted. Now, interconnected fractures, which are ultimately the fluids for flow conduits. So some of the areas have been sampled just to know the interconnectivity of fractures. So there is very much regular interconnectivity of fractures. So this diagram contains, this is a kind of bedding in this direction perpendicular to this marker. So it contains the bedding parallel and perpendicular to bedding fractures. This is another outcrop section which also contains very regularly patterned fractures, and there is very interconnectivity of that fractures. And then this is another section where there is the diagonal intersection of different fractures. Although these are on the outcrops, but we can also consider such kind of penetration of fractures in the subsurface as well, and then the distribution of hydrocarbons in the subsurface. So reservoir heterogeneity in the Chorguli formation, using the scheme of Chiarella et al. 2017, 3 types of heterogeneities have been interpreted: bed scale compositional heterogeneity, lithophase scale heterogeneity, and stratigraphic scale heterogeneity. So we have a lithological mix of different carbonates and clastics. So we have one of the lithologies called as a malt, and it is a mixture of clastics and micritic material. So it is actually considered as a bed scale compositional maturity, heterogeneity. And then we have a lithophase scale heterogeneity. So on this outcrop, there is variation in the color, and based on the weathering profile, we can interpret or deduce that there is some kind of variation which can be considered as a lithophase scale heterogeneity. And then this is another section. To the right, we have the Chorguli formation. So wherever there is a red arrowhead, it shows the shaly layers, and the rest is the limestone. Ultimately, it leads to the lithophase scale heterogeneity. And then we have the stratigraphic scale heterogeneity. So all of the studied outcrop sections and the studied wells, they have been compared, the lithology have been compared, and it can be considered as an example of the stratigraphic scale heterogeneity. And such kind of heterogeneities can also lead to the reservoir compartmentalization within the reservoir. So it's a diagram which shows the reservoir compartment. So and the formation above this blue line is the Chorguli formation. And conclusion. So the Chorguli formation is a potential and proven reservoir rock. Lithologies include carbonates, limestones, and dolostone. And the fracture network can greatly enhance the permeability. And there are 3 types of heterogeneities like compositional, lithophase, and stratigraphic scale heterogeneities. And these heterogeneities leads to reservoir compartmentalization. Stratigraphic traps can also be developed due to such scenarios. In that particular geological province, it is dominated by structural traps. So based on the variation in the lithophase, we can say that stratigraphic traps can also be developed. And outcrop scale geological features and petrophysical logs derived lithology portrays a good example of hydrocarbon reservoir. Recommendation: core data is recommended for confirmation of lithology in the subsurface, and the potential of stratigraphic traps should also be evaluated. These are the acknowledgements. Some of the companies, for example, Synergy has provided interactive petrophysics. Some of the organizations have conducted certain analysis, references, and thank you for your attention.
Thank you, Muhammad, for the presentation. That was really interesting. So now let's switch to the questions. If there are any questions, you can write in Q&A or just raise your hand. Maybe there are questions from the organizers.
I might have a question regarding your work. Well, first of all, thanks for the presentation. It was very interesting, and I might maybe I got lost somewhere, but I wanted to ask you if you have some, if you had also seismic data, seismic perspectives, or any indirect measurement that Cool.
No, I haven't got any seismic data.
Okay. Okay.
Yeah.
And so you're using outcrops and logs.
Yeah, exactly.
And the correlation. Okay. Thank you very much.
Also, there is not a question, but compliment from Mohammed. He writes that thank you very much for a very informative presentation and very fruitful. So, if there are not any other questions, I'm passing to Anna.
All right, thank you very much for your presentation, Mohammed. Now we are going to have Robert Neumeister with subsidence analysis of the Upper Austrian molasses basin. You can now share your screen.
Yep.
Yeah.
So just give me a second. You should now see my screen.
Yep.
All right, cool. So then, first of all, thanks very much for having me today. And I would like to give a talk about the hunt of the slab breakoff in the upper in the alpine subduction zone, or in more scientific words, the subsidence analysis of the Upper Austrian molasses basin. So first of all, we have to start with what are we actually doing? So as the title is already saying it, we are generating a subsidence curve for the Upper Austrian molasses basin. And with this, we would like to get to know at what time the basin saw changes in subsidence or uplift and how it behaved in these time steps. The second question is, why are we actually doing it? So why do we even bother? And therefore, we have to first understand how do falling basins even form and why they are that important. So in our case, we have here the collision of the European and Adriatic plate, thereby creating the alpine origin. And the European plate is being subducted below the Adriatic plate. And in the foreland of the origin, so of the Alps, we are creating this falling basin here. So there are three different mechanisms that lead to the subsidence of this basin. First of all, we have the topographical load of the alpine origin that is pushing down the European plate, therefore creating space at the surface. Second, we have the subduction load. So the load of the slab is pulling down the European plate, again creating space at the surface. And then last but not least, we also have a basin fill load. So the weight of the sediments again pushes down the basin and the European plate. So we can say that the subsidence in a fallen basin is mainly explained by loading and flexure of the lower plates of the European plate. And with this figure, we can now also say why our study is that important, because in the fallen deposits, we are always able to detect any changes in the orogenic collision. So with our study, we would like to get to know if there were any changes in topographic load or subduction load. So do we see any slabs breaking off or anything like this? So in other words, why are we doing it? We would like to check individual alpine collision scenarios and possibly even verify them. So let's jump into a study area. So we are here in the very easternmost part of the Northern Alpine Fallen Basin. And if we zoom in, we have here in yellow the fallen deposits. In the south of this figure, we have the alpine origin. And directly in this transition zone, here outlined in pink, we have access to a beautiful 3D seismic cube where we did our subsidence analysis on a couple of wells, some of them marked here with a red star. However, we will today stick here with this seismic line, AA dot, and we'll see the subsidence analysis of the Hochburg well. However, all of the other subsidence curves look very, very similar to this one here. So let's take a look into a geological setting and into our seismic line, which is this one here. And what we can see here that we're definitely in a foreland setting. We have in the south of this line, we have the alpine thrust front. In the lower part, we have the Eurasian basement. And then here, this beautiful triangular shaped foreland basin. And here we did a seismic interpretation, basin-wide, 3D, and came up with, all in all, 11 dated seismic reflectors. Important here is that we have our first date reflector here in light blue at 33.1 million years. And our last dated reflector is today's surface at 17.77 million years. Also important is here the Zupfing formation. So these are these deep water deposits here. Those are again directly eroded by a basin-wide erosional surface, which is the NSU, which is the northern slope unconformity. So now we are able to calculate a subsidence analysis or a subsidence curve with all of these 11 dated reflectors. And by doing so, we have to generate or calculate the initial porosity, compaction coefficient, water depth, sea level, grain density of every unit. We have to get the initial porosity. We have to decompact every layer. We have to generate a whole backstripping method here for the whole basin. I'm using this formula, and as this probably just goes a little bit too deep into the theme, and this may be also a little bit confusing at this time step, I would like to stick today with the results, and our results are mainly this mean subsidence curve here. What we can see here is the depth of the basin evolving over time. So we're starting here at 33.1 million years with our first reflector and end at 17 million years with our last reflector. We can separate the subsidence curve here in 4 different stages. However, stage 1 and stage 3 just like show these perfect foreland basin subsidence curve where we have a steady and slow increase in total and tectonic subsidence. And as this is kind of like boring, I don't want to stick into these 2 stages today, but want to discuss with you stage 2 and stage 4 as they are very, very interesting. So in stage 2, we have this huge increase here, this very huge increase and increase in subsidence and subsidence rates over a very short period of time, followed by the northern slope unconformity. So by the aforementioned erosional surface. In stage 4, we have a final uplift, a tectonically induced uplift in our basin of around 900 meters. And here I have to state one thing, because we would usually say, all right, this uplift begins here at this data point at 18.3 million years. However, we had problems with the program with which we calculate the subsidence curve. So the program still thinks we're here in deep marine conditions at this data point, which is absolutely not the case. We're very sure about this. It is very, very likely that this uplift already begins here at this data point at 19 million years. But let's discuss these 2 different stages. So in stage 2, as already mentioned, we see this huge increase in subsidence here, mainly tectonically induced, in some wells of 1,500 meters even, followed by the northern slope unconformity. Now the question is, what is the trigger for this huge increase in subsidence on a very, very short period of time? And if we take a look into literature, then this is mainly explained by the increasing load onto the European plate. So by northward extent of the Alpine thrust front and final knapsacking and crustal thickening. However, we think there must be a different process for this because these 2 processes would mainly lead to subsidence only in the 4 deep depot zone, so in the foreland, in front of the thrust front. However, there's another study that reveals that we have the exact same pattern of subsidence also on wedge top basins, so directly inside the Alpine origin. So therefore, we need to have a way more regional process that explains subsidence in the 4 deep and wedge top depot zone. And therefore, we like to give 2 different scenarios. The first scenario is the lagged response time of the lower plates of the European plate. The idea behind that is that the lower plate just needs some time to react onto the load of the Alpine origin. So therefore we have this figure here by Busby and Ingersoll. And here we can see that we have a constant load of the Alpine origin. Here we have the foreland basin. And by not adding additional load, we still see in these 3 different time steps an increase in subsidence in the 4 deep depot zone and in the wedge top depot zone. So this is the first scenario, and this may be also be additionally compensated by the second scenario, which is the so-called rollback orogeny theory, which was proposed by Kissling and Schönegger for the Central Alps. The idea here is mainly that the European slab that is hanging below the Alpine origin is rolling back, therefore increasing the slope of the slab and therefore increasing the subduction load, as aforementioned, And with increasing subduction load, we generate subsidence all over here in this whole alpine region in the eastern part. So we are generating subsidence in the foreland and the wedge top depot zone. So far about the stage 2 and this increase in subsidence. But what about this last stage uplift here, beginning at 90 million years? Again, we need to think here probably a little bit more regional, because again, if we take a look into the wedge top depot zone, we again see the exact same pattern here in subsidence, or uplift in this case, because we have here also an uplift in the wedge top depot zone. So again, we need a way more regional process that explains this, this uplift in the Eastern Alps. And therefore, we favor a slab break-off in the easternmost part of the Alpine origin at 19 million years. That generates uplift both inside the Alpine origin, unroofing of the uppermost Augenstein formation that is then peering inside into our basin. And we have an uplift of our 40 depot zone. So we have we think that we see here a slab break-off at 19 million years. And now the next question is, can we even extend our new knowledge and compare it with some other studies? So can we even extend our slab break-off here at 19 million years, maybe with the Vienna Basin and also the Carpathians? And in fact, we think that we can do this, because we have the emission of the slab break-off in the Eastern Alps here at 19 million years. Then at 60 million years, there is the initiation of a strike slip basin in the Vienna Basin. And then there are clearly evidences for a slab break-off that is continuously moving here from the Western Carpathians all the way around the Carpathians until its recent position north of Bucharest. So if we compare this, we have something around 1,900 kilometers of slab break of migration over the last 19 million years, and therefore we end up with a mean lateral break-off velocity of approximately 100 kilometers per million years. So to conclude, we have a main phase of subsidence after the Europelium-Chatrian boundary at 27.8 million years. Herefore, we give two different scenarios. First of all is the flexural response and lagged response time of the constant load of the Alpine origin. Second, we have the rollback origin theory by Kissling and Stunegger. Then we have a late stage phase of uplift with a possible trigger of a slab break-off. And we think that we are able to link this slab break-off with other studies. And therefore, we think that we see the emission of a slab break-off here in the Eastern Alps at 90 million years that is then progressively moving all around under the Vienna Basin and then all the way around the Carpathians until its recent position here north of Bucharest. And with this, I would like to conclude. And now I'm very, very happy to answer some questions and to get into the discussion with you.
Thank you very much for the interesting presentation. Does anyone have questions? Actually, I have one question. I didn't understand exactly how do you think the rollback, the slab. Oh, can you show the presentation, please?
Yeah, just a sec.
Oh, sorry.
Here we go. So
When
you probably mean
during the uplift.
Ah, the uplift. This one.
Yeah. So sorry. Yeah. I didn't understand how the uplift appears on both basins.
So the idea here is that if you remove the slab below the Alpine origin, like this is such a huge load, like this whole slab that is approximately that was or is thought to be approximately at a depth of 200 kilometers at that time. So if we remove this whole load of a slab of the lower plate of the European plate, the idea is that you not only create so that you have kind of like a bounce back of the European plate here, and thereby you create not only uplift in the 40 depot zone, but in the whole Alpine region here. So this is just such a huge event that that this uplift here would not only appear in the foreland deposit, but also inside the whole alpine origin region here.
Okay.
Hope that answers your question.
Yeah, the question was about the continental one. But yeah,
okay.
I think I understood. Yeah, thank you.
Cool.
Does anyone have another question?
I may have another question for you.
Okay.
Regarding stage 2, where you have a scenario with a rollback of the cloud, possible scenario. So this is one of the scenarios, and I was thinking that having a rollback would actually create a situation of extension of the basin. So would you expect, well, I would expect tectonic structure, extensional tectonic structure associated to this event. Do we have any information about that? Could you, were you able to point out?
Yes, we do. Just let me check this very quickly if I have this figure here. Yeah, so it didn't interpret these the extensional fault pattern here, but however you can still see it here. Like this is our another seismic line BB dot, and here you can clearly see like this is an uninterpreted version of the faults, but you can clearly see here these extensional normal faults all the way around the basin. And what is very, very interesting, so indeed we do see this normal faulting pattern. So with this extensional phase at that time, and what is very, very interesting here, that all of these normal faults are kept by this reflector here, which is the northern slope unconformity. So exactly as you were saying, we believe that the phase of flexure of the lower plate must have ended with the end of the northern slope unconformity here, as all of these normal fault patterns are sealed by it. So we definitely see this, and see this extensional fault pattern here. Very good question, though.
Thanks. Well, it was a nice presentation. Thank you.
Excellent. Does anyone have another question? Well, I don't think so. Thank you so much, Robert. We can proceed. I give my word to Turan.
You have a hand raised.
Well, I didn't see it. Where?
There, I'll unmute him.
Okay, is that?
Go ahead, Mohammed.
Yeah, good morning. Yes, thank you very much for your presentation. It was very good.
Sorry, Mohammed, I think your connection is very, very low. I can't really hear you that well.
Okay, thank you very much for your presentation. It was very good. And there is something I didn't catch up from your model.
I can't hear you, Mohammed. You're breaking up.
Yeah, I'm pretty sorry, Mohammed. Maybe it's easier if you ask your question in the Q&A section or in the chat, and then I can answer them there, because it's just like broken off. Your voice is broken off. Sorry for that.
All right. Well, doesn't look like we're gonna get his question, so we'll turn it back and move forward.
Yeah, thank you, Lori. So thank you, Robert, for such a great and interesting presentation. And now we're moving to our last and fourth presentation in session number 3 by Ross Armstrong and Emmanuel Alokem from Uppsala University. And they will talk about comparing airborne magnetic techniques for mineral exploration at the Blotberget iron oxide deposit.
Yeah, thank you very much. Everyone, can you hear me?
Yes.
Okay, good. So my name is Emmanuel, and with me is Ross. We are both master students from Uppsala University, and we are going to be discussing with you our result from comparing different airborne magnetic techniques over an area in central Sweden. But first, let's go through a little bit of background. Human interaction with natural resources dates back in time, so much so that we have different periods in our history named after different natural resource. And you would agree with me that we have come to a stage where we can call it the critical materials age, where the resource footprint needed as an individual is far greater than the resource footprint needed by a community back in the 1700s. If you combine this with the soaring global population size, for instance, between 2000 and 2010, there was 1 billion increase in the population side. When you combine this together, you begin to see the grim reality of our resource footprint as a people. If we go over to the EU, it recently published 30 materials which it named critical, based on the importance of these minerals and the risk associated with securing the supply. The chart here, you can see the economic importance is increasing to this direction, while the supply is going in this direction. And you can see in red, these are the so-called critical materials. And these materials are evolving over the years. For instance, between 2017 and 2020, bauxite, lithium, which is one of the core ingredients for e-mobility, for instance, and titanium moved into the critical region, while only helium moved out. So invariably, you can see that there's an increase in the number of critical metals from 2011, when the first publication was done, to 2020. If we go over to the global west, we go to Canada and we discover that most of these materials are also published as critical. As a matter of fact, we have 31 of them also for economic security and transition to low carbon economy. So we can begin to see that this is a global issue, the issue of criticality of resources. Now let's take a look at the existing global supply chain. A quick look at this and you can already see the monopoly of China over the rest of the world. And if I add these remarks, it pretty much sums up the socio-political disposition of this region. Like China, obviously, as the biggest supplier, can decide to do anything they want any day. So we are out at the mercy of their mood swing. Of course, you can go to Africa, but you're going at your own risk. Meanwhile, Europe claims not to have any, a claim which I feel that is arguable. In the US, they want to mine more. And there are also some solutions, like for instance, in Japan and in some other rest of the world. And this solution, I deem it temporary. And why do I deem it temporary? Because it only assumes it's circular economy, as you can see, and it involves keeping the existing material in a loop. But this is only temporary in the sense that, except you're dealing with a donut economy, where we do not expect economic growth, that is when this solution can be feasible in the long term. But to account for the economic growth, which is inevitable, we need to intensify effort on exploration and mining. And this invariably means that we all have to go back to our backyard to get whatever thing we need out of there. However, going to the backyard is not as easy as it seems. Especially in the European and American backyard, there is NIMBYism. And what is NIMBYism? It is not in my backyard. It's a social propaganda against infrastructural development within residential vicinities of people. Although this is a problem, there are also differing opinions which creates like a silver lining. Like some other people are saying, if not in our backyards, then where? And this means that more, and a recent survey by the EU shows that more people are willing to accommodate this infrastructural development, provided that there is technological improvement to curb the negative externalities that arise from this project. UAV-based survey is gaining traction already in the exploration and geoscience world, and this is the basis for our study. We asked ourselves, why not test this new kid on the block? And that was exactly what we did. To do this, we accessed data from different airborne magnetic surveys done by flying helicopter, fixed-wing aircraft, and UAV with magnetometer attached. And this was done over a 50-year period of the same area, with the simple aim of comparing how the UAV-based magnetic survey will do in comparison to the more conventional, traditional airborne methods that we're used to. Our study area, it's in Ludvika, like I said, central Sweden, as you can see on the map. And if you zoom in, you can see the exact site where we worked on. This is Blåberget. And this area mining has been going on for centuries. You can see this is a picture from 1912. But operations stopped in 1979 due to the decline in global iron ore price. Again, in 2008, a new company, Nordic Iron Ore, has rejuvenated efforts to reopen this mine. And we chose this site because we have historical and recent researches that we have to go ahead with our study. And from these researches, we know so far some interesting geology in the area. We know we are dealing with an apatite-bearing iron oxide deposit, which is deepening southeast towards the depth of about 850 meters. And we also have core log sections to corroborate, to validate this model. And you can see that from about northwest to southeast, you can see where the economic mineralization occurs, and it is increasing in depth as we go towards the southeast. Interestingly, we know that this body consists of areas of different ore minerals, the magnetite-rich region and the hematite-rich region. And these two regions provide good magnetic susceptibility contrast, which is needed for delineation in a magnetic survey. Now, as a refresher, different bodies with different susceptibility will give different responses. And what is magnetic susceptibility? It is the ability of a material to become magnetized when brought in contact to a magnetic external field. And in this case, the external field is the Earth's magnetic field. So for each body, when we say we measure the response, we're actually measuring the induced magnetization of that body and also the Earth's magnetic response in that area. So we are measuring the total field strength. And the greater the susceptibility between two bodies, the higher the amplitude variations that you can see, like from here, the lowest, going to this, you can see this response. And from this body to this body, you can see the response. So this is basically the principle that is guiding our study. Now I'm going to hand over to Ross to walk you through our beautiful discovery and conclude.
Thank you very much, Emmanuel. So with our goal to compare these different airborne magnetic methods, we first had to prepare the data. Our starting point for this was the UAV data set, where total magnetic intensity, the total field strength, was measured along these flight lines here. Then, using the exact coordinates of these sampling points, we extracted the total magnetic intensity from maps of the previous aeromagnetic surveys using the Sampler Grid tool in Oasis Montage. And this provided us with 4 co-located data sets of total magnetic intensity. But are we ready for a fair comparison between them? Well, not quite yet. As you can see in the initial plot of the UAV data, we have these outliers that are associated to the landing or takeoff of the drone. But by excluding these 10 points, the 3-dimensional plot of the UAV data returns to a scale that's comparable with the other data sets. And just to clarify exactly what we're seeing here, we have easting and northing plotted on the X and Y axis, meaning that in this configuration, in this example, north is in this direction into the screen. And we also have total magnetic intensity plotted on the Z axis, ranging here from 52,000 to 60,000 nanotesla. And if we take a look at the results, we see a general agreement between all of the plots. In each of them, we have this northeast-southwest trending region of anomalous magnetic highs, though with varying amplitudes. And we can also see the southeast dip direction of the ore bodies, which is indicated by this gentle downward sloping of magnetic intensity towards the southeast. But perhaps the main difference that we see in these results is an improved resolving ability through time, something that can be best observed by looking at these plots in chronological order. So first we have the fixed wing data from 1972, then from 2016, the helicopter-based magnetics, and the UAV data from last year. From the oldest results alone, we might infer the presence of 2 separate and distanced magnetic bodies. However, with the newly acquired UAV dataset, the true complexity of the ore deposit is much better reflected. We have these distinct double peaks in magnetic intensity that can be attributed to the different causative bodies in the subsurface. And from this, we can then start to try to distinguish between different zones of mineralization in the subsurface, which of course have different distributions of magnetic susceptibility, the physical property. So we have this improved resolution, but it's important to note our caution in comparing the absolute values of magnetic intensity between the data sets, because there are numerous non-geological factors, such as the different flight heights of the surveys, that trade off and contribute in different ways towards the magnetic intensity that's measured. But moving on, we also compared the total magnetic intensity on a one-dimensional plot, taking into account all of the data points. And it's here that we can best present the true significance of this study. And to make this point clearer, we first applied a smoothing filter in order to remove any non-geological noise from the end of the survey lines. Now, the simple beauty of these results can now be seen, where we have the UAV survey, which is shown in red here, that performs equally well in detecting the same trend, so the same highs and lows in magnetic intensity as the fixed wing and helicopter surveys. And it's this replication of the magnetic signal that is the main takeaway from this study, because its comparable performance completely validates this novel and innovative approach relative to the more conventional and trusted airborne methods. But what exactly are the future implications to this validation? Well, we can now start to recognize the use of UAVs as a viable approach for mineral exploration, which also has the added value of sustainability, which is a crucial enabler within this current context of NIMBYism and other socio-environmental hurdles that the mining industry has to overcome. And by targeting and promoting all three pillars of sustainability, the use of UAVs will facilitate more mining and mineral exploration efforts. And this will allow us to tackle the criticality of the raw material value chain, while also promoting the energy transition by allowing us to meet the resource demands necessary for producing renewable energy, e-mobility, and other clean technologies. So to quickly summarize, our comparison of the airborne magnetic methods from Blockberry showed that through the evolution of these different surveys, our ability to delineate the ore bodies improved through time, which culminated nicely with these distinct double peaks observed in the UAV data. But more importantly, however, through this simple 1D plot, we validated the use of this UAV mag system for mineral exploration in a cost-efficient, non-invasive, and socially accepted manner. So we think that this study should be taken as inspiration for companies within the mining industry to be early adopters of innovation and know that this sustainable approach to mineral exploration using UAVs doesn't have to compromise the quality of their results. So thank you very much for listening, and yeah, now we'll be happy to answer any questions you have. Cheers.
Thank you, Ross and Emmanuel. I really liked your presentation. So if anyone has any questions, just type in Q&A or ask directly by raising the hand.
There's a question that wants to know when did their oh, never mind.
Yeah. So maybe someone from the chairs want to ask something.
Yes, I have a question. Yeah, I know that these results are quite new, and I guess this drawing is also quite new from the year of the study. But I wanted to know if there is already some prospect to use it in another site or do a new study with this technology.
I don't think, within the smart exploration program that these geophysical surveys were performed within, that project's just come to an end actually. So I think there's nothing lined up to use the exact same system. I think what my thesis is actually kind of a continuation from this work, where now I'm going to be using the magnetic data from the UAV to integrate it and perform an inversion with it and make these magnetic susceptibility models. So I think if once that's published, and hopefully this all works towards the company that's trying to reopen this mine, Nordic Iron Ore, hopefully this all enhances the feasibility of the mining operation if they can reopen the mine by incorporating this UAV data as part of their research, then yeah, hopefully it will just act as encouragement for other companies within the industry to start thinking, oh, we can also use a UAV. Like, we don't have to pay like so much to get this consultancy firm to get their helicopter over to like the north of Sweden or something. Like, more companies will adopt this way of thinking, and I think this UAV system, even as it is, it's getting really good results. So I think it's definitely applicable in other cases, and it's just about kind of making sure the success of this case study is promoted.
Yeah, and if I may add to that, you know, just like any new technology that has been introduced, you know, if you remember when the car was introduced, there's always this entry barrier, like people thinking maybe it's not going to work. But as more people try to work with it, then they realize, okay, this is just a better way, a more efficient way of doing things. That said, if you look at UAV, one of the pros of using UAV is that you get to go as low as you can without violating any serious rule. But imagine if you would have someone flying that low with an helicopter near you, then it's going to be like a kind of disturbance to you. And the fact that it can fly so low, it can even go and maneuver in places where you don't have an open field. So the pros are quite, you know, unlimited, you know, and the cons also, they are not, one of the cons that we just discussed are things that you can easily remove, and with time, they're going to smoothen it out over time.
Yes, for sure. Thanks a lot. It was a very interesting presentation, and hopefully these results will encourage the utilization of this technology.
Thank you. So, are there any questions? Any other? We have only one in Q&A, but that's more like a compliment. Thank you guys for this geophysical method, which is friendly to the environment. So if there are not any other questions, we're going to the 5 to 10 minutes break just to wrap up everything, and we'll come back to you just to announce the winners. Thank you.
Okay, see you after the break.
Thank you, everyone.
Well, first of all, thanks to everyone for, thanks to all the presenters for their presentation. They were all really interesting, all of them. And I have to say, I think I speak for everyone, for every other member of the committee, that it was an hard decision. Thanks to the audience for being here. And I think we can already start with the announcement of the first 3 positions for the first three projects. So we decided, starting from the 3rd position, we gave the 3rd position to Malin Lunde with their project on constraining carbon turnover in Arctic and subarctic sediments using pore water carbon isotopes. The 2nd prize, second position, goes to Neumstar Robert, and with a subsidence analysis of the upper Austrian Mollusk Basin. And the 1st position goes to Deborah Wiener with her study on deciphering Southeast Asian tectonics as an introduction to full wave inversion in seismology. So thank you all for participating. If you have anything to declare, anything to say, feel free. And if Turan has anything else, I will leave
Thank you, Roberto. I would like to congratulate guys, students, for the places, and for the rest, you really did a great job, and all of your presentations were really interesting, and I learned a lot. I'm talking about myself, but I guess the rest of the members of the committee also will agree with me. So again, congratulations, and thanks everyone, to the participants, the members, the students, for being with us today. And have a nice day.
All right. Congratulations again to everyone. And I think we can now close the event.
Thanks very much for organizing it and hosting it as well.
Thank you very much, everybody. It's good to meet you. Bye.
Thank you.
Thank you. Bye.
Bye. Bye.